Mega Mechatronics.
Welcome to the Mega Mechatronics Bootcamp series for mechanical engineering. We're covering topics in materials. Today we are looking at hardening and treatments, heat treatments, and even some cold working processes. So when we're hardening a material, we're hardening a metal, we're going to crystallize it, we're going to let those atoms move around, and then we're going to cool it. And then those atoms are going to start forming crystals. And at the microscopic level, for ferrous materials, aluminums, we're looking at a cubic structure. And there's body center cubic and face center cubic. So the body center has a atom centered within the cube, and then a face center cubic where there's atoms centered on the faces around that cube. And there's even hexagonal for some other materials and things like that. So looking at the dynamics of the crystal structure, so imagine this is a structure of those cubes, and we can move those things around and it won't break or fracture because the atoms are bonded together by kind of like a magnetic force. So if you shift that over, if you plastically deform it, those atoms are going to latch on to an adjacent set of atoms and move around. So if we watch this video of these magnetic ball toys, it's sort of illustrating that, where he starts deforming it, but it stays clumped together. The balls moved their position, but it still found something to latch onto, a similar atom. And when this happens, when these crystals start forming randomly within the material, they're going to be crystallizing in different orientations to each other. So you see this is an example of a galvanized surface, and that zinc is crystallizing in different orientations, and then we see the light refracting off of that in different ways, and then we can easily make out the grain boundaries. So looking at a computer-generated model, you could sort of see the crystal structure, a uniform grain, and then those grain boundaries around there. We'll zoom in even closer, sort of outline those, and then give you an idea of the different orientations. And the size of the grain boundary is definitely important. So if you have smaller grains, more smaller ones, that's going to give us a stronger, harder material, because we're reducing the ability for those grains, for that crystal lattice to deform and move around, because there are these deformities there, sort of like a wall stopping them from moving any further. And then on the other side of that, if we have huge grains, and that makes the material more ductile, because we're allowing it to move around and deform and allow those cubic structures to move around and reorientate themselves and shift around. And the concept of hardenability, different alloys of metal are going to have different abilities to harden, a different max hardness that you can achieve. So with ferrous materials, we put carbon in it, and the carbon will increase the strength. It gives certain characteristics to this crystal structure as it's in there. It deforms it in a certain way and allows us to harden that material by controlling the crystal structure. So looking at this chart, we have a hardness versus carbon content. So you see the Rockwell C hardness scale goes up as the carbon content goes up. And the hardening recipe is very important of the time and temperatures that the material sees during the hardening process. So let's look at if we had the scale here from ambient temperature up to transformation temperature, which could be 1600 degrees Fahrenheit for certain steels, but it all depends on the alloying elements, and then that versus time. So we heat it up, quench it, and then we'll do a little temper here. So the heating rate's important. The time at temperature depending on the thickness of that material and, of course, the alloying elements in it. The cooling rate is very important. What the cooling rate does, what the quench does, is it locks in a certain crystal structure, desirable crystal structure such as martensite. So different quench medias that are used could be straight water, water with additives like polymer additives, oil, and even molten salt. So the recipe is going to lead to success if you can follow that recipe consistently, or if you figure out the perfect way to bake those brownies or whatever you're making, and do that consistently, will give you huge advantage. Like in racing, valve springs, it's extremely important. The processes that spring goes through, because it is put under so much stress. Stress is higher than the material specifications. That's because it's been post-processed and maximized. So again, looking at this chart, an example process for a high-performance valve spring would look something like this, where there's a hardening, there's an oust temper where we're not bringing that all the way down to room temperature and we're not quenching it, and the quench rate is a little bit slower because we're dipping that in some molten salt and holding it at a higher temperature. And then after that, we're going to even bring that below into sub-zero cryogenic temperatures to complete the transformation of martensite. So any retained austenite will turn into martensite. And then, of course, there's a lot more processing that goes into the spring. This is just the beginning of that, of building a high-performance spring. So looking at some phase transformation diagrams, this will give engineers an idea of where to start with what temperature. And this is carbon content versus temperature for a carbon steel. So you see the different crystal structures within this chart that can be achieved at different carbon contents versus temperature: austenite, ferrite, pearlite, cementite, and there's other ways to even get bainite with some other post-heat treatments. And aluminum is going to be a little different. Here's a phase diagram. Temperature versus composition of silicon, not composition of carbon. Carbon is for hardening ferrous materials. Silicon affects the hardness of aluminum. Same with other elements like copper, depending on the alloy of aluminum that you are using. So looking at different compositions, here's a plain carbon, 0.17% carbon, and another material, but that's not really an alloy. This is an alloy right here, 4130 alloy, because it's got more than two elements that are alloying it. And what makes this special is the silicon, chromium, and molybdenum, the nickname for this is chromoly steel, and this is what you build race cars out of. It is a very high strength, ductile, strong, tough material. And then let's look at 304 stainless, 20% chromium, 1/5 of that is chromium, which is extremely hard, and these elements will create that protective layer and give stainless steel that reputation for being such a corrosion-resistant material. So out of one alloy, we can give it many different properties. So imagine this is one type of metal, one type of alloy with certain elements. We're not changing anything. The only thing we're changing is the treatment. So A, as quenched. So this is straight out of after you heat it up to crystallization, you quench it in that water, and it's super brittle. It is strong, but it's so brittle. And you don't want to leave it, especially in a manufacturing environment when you're moving parts around. You don't want any cracks to form, people banging stuff around on the high-low truck. You need to temper it, any temper. So let's say we do a low temper where it's at a lower temperature or shorter time or a combination of both. Here's maybe a higher temper where you are bringing it up to a higher temperature and you're leaving it there for longer. And here's possibly a normalized material, and then a full anneal where you're resetting it. And you can see the wide range. So anything in between A to E, you can give that property to that material, and that all depends on your application. So looking at tempering a little closer, this is again done after hardening. The material is too brittle, and it's done below the transformation temperature. Looking at normalizing, for ferrous-based material, we're going to actually heat it up to that transformation temperature. We are going to crystallize it, but we're going to air cool it. So that's the cooling. So we're bringing it up to hardening temperature, but we're not quenching it. We are air cooling it, and that's going to give us different crystal structures. Annealing. Again, we're going to heat it up. We're going to hold it up. Hold it at that temperature, up at crystallization, but this time we're going to control that heat cooling rate. We're not just going to leave it in the air, we're going to actually leave it in an oven, and then we're going to taper down the temperature. And this is going to give it, again, different crystal structures. It's going to allow the grain structures to build and grow, and that's going to give us a softer, more ductile material. Precipitation H hardening. This is something you're going to do with aluminum, although some stainless metals will do it, and magnesium, zinc, and other things like that, non-ferrous. And what we're going to do is we're going to precipitate the alloying elements within that, like clouds forming in the sky. These particles create defects in the material, and it's actually going to improve the strength. So 6061, you weld it. You're going to lose that strength, but then you're going to age harden that thing, and then you're going to get that toughness and strength back. So how do we quantify hardness? Well, there's several different ways, but the concept is the same. We're going to, here's an example of taking a hardened steel ball. We're going to press it in with a standard force into that material, and we're going to measure the diameter of that indentation, so that we're going to pull that ball out and then measure how big that circle is. So you would imagine harder material, the hardened steel ball wouldn't go in as far. If it was a soft material, it would go in much farther. Therefore, the diameter would be bigger. Here's a Vickers test using a diamond head. Same concept. You press it in with a known test load, and then we're going to measure the geometry of that indentation. And here's an older style using it's a penetrating method. We're going to give it a minimum force, a minor load, and then we're going to give it a major load. So we're going to measure that change from how far that penetrator drops into the material between the minor and the major, and that's going to give us an indication of the hardness. So the deeper you go, the softer the material. And then looking up at an actual measurement here, you see that diamond shape left in that material. And here's a Knoop test using sort of an elongated diamond shape. And each of these have different hardness ranges and accuracies. So one test might be accurate in a harder material than another test being more accurate in a softer material. And there's even a test where you bounce a ball and you measure how high that hardened ball bearing bounces off the material. So the harder it is, the higher it's going to bounce, because the softer one's going to absorb some of that energy, and the ball's not going to bounce as high. And you can even compare the hardnesses. If you have two different materials and you're Googling the charts, you can take a Rockwell C measurement and compare that, cross-reference that to Brunel or Vickers. And you would just want to Google the comparison charts or the cross-reference charts. In a very simple way, depending on what your project is or how quickly you need to figure it out, you can just do a scratch test. The harder material is going to scratch the softer material in most cases. If there's a big difference, if there's a part that's supposed to be hardened, you can just scratch it up and see if it leaves a mark or not. Don't do this on critical surfaces, but this is for just a quick method. So that crystal structure, FCC, BCC, will affect the ductility and toughness. at different temperatures. So at low temperature, we hit on this in the last one, in ductility, I mean. So low temperature performance is related to the crystal structure. Body-centered cubic crystal structures experience that ductile brittle transition. Face-centered cubic structures retain the ductility at low temperatures. So the T1000 is clearly body-centered cubic when he was fractured in that way. And looking at the chart again, as we touched on before, so you see the copper is a face-centered cubic. It's not affected by temperature. And that this is related to that crystal structure. And you see the mild steel is highly affected. It does have the ductile brittle transition. Now let's look at localized hardening. And there's lots of advantages to localized hardening. Here's some examples. An induction hardening of a shaft. So you see it's going through that inductor ring, and it's using electricity and magnetic forces, and it's heating up just the surface of that material, and it's actually dropping into a quench tank right there in one process. And what that's going to give you is kind of like an eggshell effect, but it's not going to be weak like an eggshell. So you're going to have a very hard surface. You're going to have a very tough and durable core to take impacts and prevent fatigue failures and things like that. But you have a really nice wearing surface. And then we have nitriding and carburizing, where we're infusing nitrides, or we're infusing carbon, because remember, carbon content affects the hardness. So we're going to heat that material up in a special chamber that has an atmosphere filled with carbon, and that carbon is going to infuse into that just the surface of the material when you heat it up. So again, strong shell, tough core. So let's look at, this is hardness versus depth, and this is nitriding at different temperatures. So the content of the atmosphere within the chamber will affect it, as well as temperature. So you see that actually the lower temperature gives you a higher hardness, but at a lower depth. And then as you raise the temperature, that the nitrides can infuse much deeper into the material, but it doesn't give you a higher max hardness. And here's a close-up view. So you see that white layer is a different crystal structure, so it looks a little different, and we're getting up a little closer. You see those grains, and you see those different, you see the light grains and then that dark, and those are different alloying elements and things like that, and even the shaded. And then you can see that nitrided layer with again a different structure. And smaller grains, you can't see the grains. Here's a cutout of a gear. And this is definitely advantageous for gears, because you need a nice hard wearing surface, but you don't want those gear teeth to fracture off, so you need really tough. And these go through a lot of cycles, so there's a lot of fatigue that the gear teeth are seeing. So you need that tough core. Cryogenic treatment did touch on this. It transforms the retained austenite into martensite, and this will help promote the uniformity and strength. So liquid nitrogen, you're looking at about -300 F, and the mechanical, like super refrigerators, can even get down to a -100 degrees. So hardness does correlate with the strength of the material. There is definite correlation. So we're looking at strength here, ultimate tensile, and then the hardness at the bottom. So as the hardness goes up, so does the strength. And you'll see this with tests, specific tests of different alloys, if you were to research that. And as well as hardness versus toughness. So same concept, joules of energy absorbed in hardness. So the harder it is, the more brittle and the less tough it's going to be in general. But again, it depends on the alloy. Now let's get into cold working. This is a type of work hardening, but it is changing the structure and the grain and the dislocations and how those crystal lattices are interacting with each other. So it's definitely relevant. And we're going to use compressive forces. We're going to plastically deform the material. We're going to physically change it. We're going to permanently move things around. And we're going to create those desirable dislocations. We can improve that yield strength, but we do reduce that ductility. So here's a look at a cold rolling process. And you've probably heard this before. If you go buying materials, cold rolling, you could see that material entering between rollers that's exaggerated. There's probably a series of rollers that gradually get smaller and smaller, but you see how those grains are affected. They're elongated and they're stretched out. And actually, most of the time gives the material tighter tolerances, as opposed to a hot rolled material that might move around and change. The cold rolled material will actually hold tighter tolerances as stock, but it does contain residual stresses within it. So if you were to machine one side of that, the material will relax and move around and bend. So that is one disadvantage and something that you should be aware of. Cold heading, this is a process of putting the head on a bolt. So you see that die comes down and plastically deforms it. And it does work harden that head and make it a little stronger. In more localized work hardening examples, shot peening. So shot peening is totally different than shot blasting or sandblasting, because we're using very tight specification spheres of hardened material. So we're going to accelerate those hardened spheres, and then they're going to transfer their kinetic energy into that material, and we're going to create these compressive stresses on the surface. And much like that cold rolling, we're going to sort of do that where we're changing at the surface. We're moving those grains around and stretching them and putting these residual stresses or transferring residual stresses into it. And you can't achieve this with sandblasting. That's abrasive, where you're actually removing the surface. So shot peening doesn't remove the surface. It's working the surface. Roller burnishing, that's another example where you have a hardened ball and you're applying force while the workpiece is moving. And then again, you're putting that compressive stress in there. You are work hardening the surface. And here's an example of a material on a lathe. And you see that tool up there is pressing against it as it's spinning, and it's going to transverse along that, giving it a nice surface. And then touching on compressive stresses, why those are important. If we look at on the very left, a material, let's say it has a little crack in there, but if there are compressive stresses, everything's trying to push things together. Those compressive stresses are pushing that crack back together. So when you apply that load to split that crack open, there's actually compressive stresses countering that, and that's what gives it fatigue strength and things like that when you shot peen a part or roller burnish it. More work hardening, hot forging. So this is like cold working, but it's done at higher temperatures, and it's going to give you different characteristics. And it's typically stronger than an equivalent cast part. If you're making a part by a casting process, this gives it totally different characteristics. So here's traditional forging. We're making a sword, the guy's hammering it. And then here's a forging press, where you put a preheated metal billet in there so the thing's red hot, and then you go down and you smash it. And so because it's at a higher temperature, it is much more ductile and workable. And a huge advantage, especially in fatigue strength, is the aligning the grain structure to the shape of the part. So here's an example of a machine part versus a forged part. So you see the forged part, how the grains follow the contour, the outside contour, but then the machine part has the grains ending at critical points where cracks can form. So here's a little tip on how to spot a forged part. So let's say we're making a connecting rod for a vehicle, and we're going to be looking at the flashing. So this is that extra material after that press came down and formed the part. There's going to be some metal that flows out, some extra metal. And they're going to have to grind that off. They're going to have to cut that off and grind it down. So that's what you look for. You look for those machining, those grinding marks. So if we look at this finished connecting rod right here, you could see that really wide, very wide. So cast part, it's going to have a thin line. It's going to be the thickness of an envelope. Okay, this is much thicker. This is like 1/4 of an inch wide, and you see the grinding marks from putting it through a sander or something. A cast, they're not going to clean. They're not typically going to clean those up, and it's going to be a very thin line. So that's one way if you're buying a part or something, you can tell right away if that was forged or not. Well, that concludes our heat treatments tutorial. Thanks for watching.